Hello everyone, welcome back to another video for this one, numbers 34 through 38. 2 points on a merry-go-round are located a distance from the center, R1 and R2. So for an example, merry-go-round being a circle, we'll have R1 being the location of the first one, and R2, let's just pretend that's the full distance. So they're in a different distance location from the center. So where R1 is smaller than R2. Well, did that part right. Now, while the merry-go-round going is the process of speeding up its operational speed, so it's building up speed, which of the following equations involving magnitudes of angular speed, angular acceleration, and tangential speed for these points is incorrect? Okay, so you got to remember, angular speed is how quickly it's rotating. So it's how many, if you take a circle and you break it up into angled chunks, okay, like this is a 15-degree angled chunk or something, how many degrees is it going around per second? That's angular speed. Tangential speed, or regular velocity, is actually how fast a single point on this circle will go. So if this is spinning, this point is traveling with some regular velocity at a direction perpendicular to the radius. So that's what the regular velocity is. And what was the other thing? Angular acceleration. Now, angular acceleration is how quickly it's speeding up in angular speed. So all three of these things should be increasing, except, actually, no. The velocities should be increasing as we accelerate. The acceleration should be remaining constant. So which one of these speeds is correct? Omega 1 is equal to omega 2. So the question is the angular velocity of this point, how many degrees it goes around per second, the same as the angular velocity at this point? The answer is yes. Basically, if the whole thing was to rotate one time around, then that's, and then the other one would also rotate one time around. So they are kind of locked in like that, where a full rotation they don't get any further apart or anything during that. So the angular speeds are going to be the same. The angular accelerations, again, they're going to be the same. Oh, I'm not sure why I circled this, because it's asking which one isn't correct, and that was clearly correct. The angular accelerations are going to be the same for both of them in the same way that the angular speeds are going to be the same. The tangential velocities are not going to be equal, so that will be our answer, C. That's because the further away you are from the center of the circle, the faster you're going to be moving. Let me give an example. So if you have a dot here and a dot here, and they complete one lap of this circle in the same amount of time, one will finish this circle, and the other one will finish the whole circle. So in the same amount of time, this outer one, the one with the larger radius, is going to travel a farther distance, which means it's going to have a larger v. But it will have the same angular velocity, and it will still have the same angular acceleration. So the answer is C. A car is going around a racetrack at constant speed. The curves around the track have different radii. In which turn is the magnitude of the car's acceleration greatest? So racetrack, constant speed. The curves around the track have different radii. So it'll look something more like this, where you've got one turn with a really small radii and one turn with a really big radii, something like that. Okay, in which turn is the magnitude of the acceleration greatest? So is the angular acceleration, is it angular acceleration or just centripetal acceleration? In which turn is the magnitude of the car's acceleration? Okay, so the car is maintaining a constant speed. I assume it said that. Yeah, constant speed. So the question is, if we looked at this circle, we looked at this circle, then we would have a centripetal acceleration going this way, because remember, centripetal acceleration always points toward the center of a circle, and centripetal acceleration going this way. Now, which one's going to have the larger centripetal acceleration? Well, the answer, I believe, is the one with the smaller radius. Let's check this out first, though. Okay, so in order to make a more gradual turn, you would have to accelerate much slower than if you had to make a really, really short turn. Okay, because if you think about it, your velocity going this way, okay, can be one value, and then in a short period of time, it's going to be the same value just in a slightly different direction. Over here, your velocity is one thing, and then in a short period of time, you're going the complete opposite direction, which means you've accelerated quite a lot. So I'm going to say the acceleration is largest here in the smaller circle. Let's see if we can figure that out with an equation. V squared over r. Okay, so the smaller radius, yeah, so if you have a smaller radius here, this is the equation for centripetal acceleration. If you have a small radius here, then you're going to be dividing by a smaller number, which means the acceleration will be larger. So, it is greatest to turn with the smallest radius. That's option B. Now, an A 12 centimeter or 0.12 meter radius grinding wheel takes 5.5 seconds to spin up from this speed of 2 rads per second to 11 rads per second. What is the wheel's average angular acceleration? So angular acceleration has the same equation as regular acceleration, except we're using angular speed final minus angular speed initial over time. All right, so let's plug in. We have 11 rads per second minus 2 rads per second divided by 5.5 seconds. And I don't think we need the radius to solve this problem. I think that's extra information. 11 minus 2 divided by 5.5 gives me 1.64 rads per second squared. Please tell me that's one of the options. It is. Fantastic. We have C. All right. So starting from rest, a wheel undergoes constant acceleration, constant angular acceleration, for a period of time t, capital T. At which of the following times does the average angular acceleration equal the instantaneous angular acceleration? Okay, so here's the idea. Okay, so if we start with one angular acceleration and move to another, the average of that will be the average of that will be the average. The instantaneous could be any value in between. So example, if we started off with a angular acceleration of 0, and then we went to an angular acceleration of 5. Okay, let's pretend this is the initial. This is the final. The average will be 2.5. Okay, I think that makes sense to everybody. Okay, average is represented by that little line above it. So in this case, the average is 2.5, but the instantaneous could be any value at any given time, depending on what time you want to know. So that's obviously, there's at one point the instantaneous value is 1, then 2, then 3, then 4, then 5. Just depends on what time we're talking about. So starting from rest, a wheel undergoes constant angular acceleration for a period of time t. At which of the following times does the average acceleration equal the instantaneous acceleration? Well, to me, it looks like if this was time equals 0, and this was time equals whatever the period is, then we would be right here in the middle between the two. So that would be time equals 1/2 t, which is an option. Okay. Now, it's literally that easy sometimes. Okay. A 0.15 meter radius grinding wheel starts from rest and develops an angular speed of 12 rads per second in 4 seconds. What is the average tangential acceleration? So basically, they're giving us a bunch of rotational numbers, and they're asking for a linear or tangential number. So they're looking for regular A. And so the easiest way to get regular A is to find angular A and multiply it by R. We can do that. So starts from rest. So we have an initial angular speed of 0 rads per second. And we have a final of 12 rads per second. And then we have a time of 4 seconds. So now think about a regular equation like VF equals VI plus AT. That's a tangential or a linear motion equation. We can change that to a rotational one, literally just by swapping out the velocities and the angular acceleration. Now we can solve this for angular acceleration. So alpha is equal to final angular velocity minus initial angular velocity divided by time. And so that's going to be 12 minus 0 over 4. And so that means the angular acceleration is going to be 3 rads per second squared. Now we plug that up here, and now in the earlier problem, the radius was not required. In this problem, it is. So regular acceleration is equal to 3 for the angular acceleration multiplied by the radius, 0.15 meters. And so we get this answer, 3 times 0.15. That's 0.45 meters per second squared, which is right there.